Good afternoon. In the previous lecture, we have seen the inclusion-exclusion principle. Along with that, we have seen the principle applied on two sets and also on three sets. So this is the formula for the exclusion-inclusion principle on three sets. That is, if we have sets A, B and C, then A union B union C will be equivalent to A plus B plus C minus A intersection B minus A intersection C minus B intersection C plus A intersection B intersection C. That is, these three are the ones we are adding thrice, so we are removing them, and then this part is being excluded every time we are removing these, so we have to add this part at the end. Okay, so this is the formula. Now based on this, we'll see an example. So we have a problem. From a total of 50 students, 30 know Java, 18 know C++, 26 know C sharp, 9 know both Java and C++, 16 know both Java and C sharp, 8 know both C++ and C sharp, 47 know at least one language. Okay, so the total number of students is 50. So if we are drawing this in the form of a Venn diagram, then your total number of students will be represented by the rectangle. Here 50, which is the universal set. Then each of these Java, C++, C sharp can be taken with the help of an example, with the help of a set A, B and C. So the sets will be represented as the following A, B and C. Now after that, we know that 47 know at least one language. So these entire three circles value will be 47. That is A union B union C is 47. This will be your A, B, C, and then both Java and C++ means A intersection B, A intersection C, and B intersection C. So let's see the solution. So what is the question now? How many know none of the languages? None of the languages means this part, the excluded region. And how many know all of the languages means the intersection of all the three circles, this part. Okay. So now let's see what we are taking the values. A is Java. A value is cardinality of A is equal to 30. Then the next is B, which is 18 no C++. So cardinality of B is 18. C is equal to 26. The set C cardinality is 26. A intersection B is 9. A intersection C 16. And B intersection C is 8. And A union B union C is 47. Why are we taking A union B union C as 47? Because at least one of the languages known by 47 students. So this entire area which comprises of all the three circles is equal to 47. Now the next thing is, if we want to know how many know all the languages, it will be A intersection B intersection C. So the formula is as follows. Before finding by using the formula, we will try to find this part. How many know none of the languages? So 47 know at least one language. None of the language means 47, 50 is the universal set, total number of students. So none of the languages will be equivalent to 50 minus 47, which is equal to 3. So the solution for this question is 3. Now, how many know all the languages? It means this part, the one I am coloring right now. So this part we need to find out. So we have been given the values. It can be written as 47 is equal to 30 plus 18 plus 26 minus 9 minus 16 minus 8 plus we are supposed to find this value, A intersection B intersection C. So this will be equivalent to 6. So I'll just clear this slide and you can see the final solution. So this is equivalent to 6. Okay, so this is the example problem. Similarly, we have another example which we will see right now. A total of 1232 students have taken a course in Spanish, 879 have taken a course in French, and 114 have taken a course in Russian. So let's just write the values. So Spanish course, I'll take it as A, which is equivalent to 1232. 879 have taken a course in French, so this is your B, 879, and 114 have taken a course in Russian, so this is C, 114. After that, 103 have taken a course in both Spanish and French, so A intersection B is equal to 103, and Spanish and Russian, so A intersection C is equal to 23, and French and Russian, so B intersection C is equal to 14. And then if 2092 students have taken at least one of Spanish, French and Russian, so there are 2092 students who have taken at least one of Spanish, French and or Russian, so A union B union C. When we are talking about at least one of the course, then it will be A union B union C. What is the total number? 2092. Now, how many students have taken a course in all the three languages? So we have to find A intersection B intersection C. What is the value of A intersection B intersection C? So the formula is, let me write the formula over here. A union B union C is equal to A plus B plus C minus A intersection B minus B intersection C minus A intersection C plus A intersection B intersection C. Now we have to find this term. So let's write it. Let's substitute the values. This was 2092 is equal to 1232 plus 879. Please refer these values from the earlier slide. 114 minus 103 minus 23 minus 14 plus we have to find this value, so A intersection B intersection C. So when we solve these, we will get A intersection B intersection C is equal to 7. Okay, so this number of students who know all the three languages is equal to 7. So this is the solution. Let's see the, so this value we have got it as 7. Okay, now let's see the inclusion and exclusion principle for n sets. So what is the inclusion exclusion formula for the union of n sets? So we have seen by now for 2 sets, 3 sets. What is the formula for n sets? That is, this formula for n sets is basically your principle of inclusion exclusion. Principle of inclusion exclusion. So let's see that for n sets, sum of sizes of all single sets. So this formula A1 union A2 union and so on up to union of an is basically given as, first we have to take the single sets sum. So how we were doing for 2 sets, we are writing A plus B. So similarly, if we have n sets, we have to write A1 plus A2 plus so on up to an. After that, we have to remove the sum of sizes of all 2 set intersections. That is, we were removing minus A intersection B, minus B intersection C and so on. So we have to remove that 2 set intersection should be subtracted. Then 3 set intersections should be added. Again 4 set intersections should be subtracted, and this continues till, if suppose if we have even number of sets, then this sign will be negative. If we have odd number of sets, this sign, the final sign will be positive. That is minus 1 power n plus 1. I'll just explain this in a bit, but at the end we will have minus 1 whole power n plus 1 into sum of sizes of intersection of all n sets. That is A1 intersection, A2 intersection and so on up to an. This is written by using the sigma notation as k is equal to 1 to n minus 1 whole power k plus 1 sigma intersection ai. Okay, so this is the formula, or it can give a formula for the number of elements in the union of 4 sets. So for this problem, let's write the formula. So for this formula, the inclusion exclusion principle for 4 sets can be written as follows. So if the 4 sets are given as A union, B union, C union, D. Okay, these are the 4 sets. Then your formula will be sum of all single sets. So A, the cardinality of A plus B plus C plus D minus the intersection of subtracting the intersection of 2 sets. So this will be minus A intersection B minus A intersection C minus A intersection D minus B intersection C minus B intersection D minus C intersection D. So these are all the combination of 2 sets that we will get when we are subtracting. After that, we have to, so for this we have taken, first we were taking the positive sign for single sets, then for 2 sets intersection we are taking negative sign. Again we have to shift back to positive sign, that is alternatively we will have a negative and a positive sign. So over here plus intersection of 3 sets, so A intersection B intersection C plus A intersection B intersection D plus A intersection C intersection D plus B intersection C intersection D. Okay, these are the all, these 4 are all the combination of 3 sets intersection, and we have to add it. We have seen already the reason why we have to add it when we were doing inclusion exclusion on 3 sets. Okay, we will be removing all these parts when we are subtracting the 2 set intersection, so we have to add it. Again when we add it, we are adding the A intersection B intersection C intersection D, that we have to remove again. So it will be A intersection B intersection C intersection D. This should be removed because it has been added over here. So now this formula contains 15 different terms. Okay, one for each non-empty subset of A1, A, B, C and D. Okay, so whenever we are taking the inclusion exclusion principle gives a formula for the number of elements in the union of 4 sets. So whenever you have 4 sets, the inclusion exclusion formula will have 2 power 4 minus 1 terms. Okay, so 2 power 4 minus 1, these are the number of terms in the inclusion exclusion formula. Okay, so if we have, so this is your final result for the union of 4 sets. I'll even have written as the form of a slide, but for now, if we have n sets and we are supposed to find the principle of inclusion exclusion, number of terms in the formula will be 2 power n minus 1. So if we have 2 sets, 2 square minus 1, 3 terms, right? If we have 3 sets, then there are 7 terms. If we have 4, we will have 15 terms. Okay, so this will go on increasing exponentially. Now let's see the result a bit clearly, the union of 4 sets. So this is the formula for union of 4 sets, A plus B plus C plus D minus the intersection of 2 sets combinations. We have 6 such combinations, and then plus A intersection B intersection C, intersection is missing, plus A intersection B intersection D plus A intersection C intersection D plus B intersection C intersection D minus A intersection B intersection C intersection D. And this is the Venn diagram. The next topic is applications of inclusion-exclusion principle. So before we see the applications and the formulas, let me explain you that many counting problems can be solved. So we use many counting problems can be solved using the principle. For instance, or for example, we can use this principle to find the number of primes less than a positive integers. Number of primes less than some positive integer z plus. Okay, so this is one application and it is very important. So this is also known by the name of sieve of Eratosthenes. And apart from that, we have onto functions. Many problems can be solved by counting the number of onto functions from one finite set to another. And this problem is also used to find the number of such functions. So onto functions from one set to another, that is finite set, obviously we will consider. And to find the number of total such onto functions, we use inclusion-exclusion principle. Apart from that, we also have this problem which is known as the heart check problem. What is the heart check problem? The problem is basically that, suppose if you are going to a movie theater and you are supposed to give your hats, every person is wearing a hat and you are supposed to give your hats at the counter, then what is the probability that no person is given the correct hat? That is, every person receives some other hat but not his own hat. Okay, so the hat is given randomly and every person who came to the movie receives some other hat apart from his own hat. Okay, so this problem, heart check problem, it is actually based on the concept of derangement. So this word is basically the opposite of arrangement. Okay, arrangement is when we arrange some object in a given order, while derangement is basically when we are arranging it in such order that a derangement is basically a permutation of object that leaves no object in its original position. That is, whenever we are arranging the objects, we arrange it in such a way that any object which is given is not in its original position. So suppose if the original position of these numbers was 1 to 3, so 1 will not be in its first place, 2 will not be in the second place, etc. So what is the derangement of 1 2 3? The derangement of 1 2 3 is either 2 3 1, so 2 is in the first place, 3 is in the second, and 1 is in the other place, or it can also be 3 1 2. Okay, both of these are derangements, while 3 2 1 is not a derangement because 2 is in its correct position. Okay, so this is basically derangement. Now let's see. This was just an overview. We'll now see the topic in detail. So applications of inclusion exclusion. So whenever we are considering this application of inclusion exclusion, there is an alternative form which we can consider for the principle of inclusion exclusion. What is the alternative form? In particular, this form can be used to solve the problem that asks for the number of elements in a set that have none of n properties. So for example, if we have a set A1 which has the property P1, a set A2 which has the property P2, and so on up to a set AN which has the property Pn. We have so many sets in between. Now, whenever we are solving these kind of problems, what we can do is, suppose someone is asking us the number of elements, the question is number of elements in a set that have none of the properties. Okay, so we are asking for the question which in a set which has none of the properties. So basically, suppose if we are defining the problem, it can be given as this way. Let AI be the subset containing the elements that have the property Pi. AI has elements which has the property Pi. So this Pi is the property. The number of elements with all the properties Pi1, Pi2. So this is their subset 2 and so on till Pik will be denoted by n of Pi1, Pi2 and so on up to Pik. Now writing these quantities in terms of sets, so AI has the property Pi, okay, so AI is a set. So the first set AI1 intersection AI2 intersection and so on up to intersection AIK. So these are the total sets A1, A2, A3. Why am I considering I? Because we are talking about some random set AI. So that is the reason I have written this AI, which will be equivalent to n of, now AI1 has the property Pi. So n of Pi1, Pi2 and so on up to Pik. If the number of elements with none of the properties P1, P2 and Pn, if you want that, then that can be written as n of P1 dash. So P1 dash denotes that it does not have the property P1. Okay. And then we have P2 dash. It does not have the property P2. And Pn dash will be the total number of elements minus the ones which have at least one of the property. So in the earlier lecture I have already told that if your set has at least one of them, then we consider the symbol union. So from the inclusion exclusion principle, what will be the formula? The formula for this n of P1 dash, P2 dash and so on up to Pn dash will be n minus A1 has the property P1, so P1 plus P2, so we'll just generally expand this formula. To understand this in a bit of detail, we will see our example of the first example that I have given. So it can be used to find the number of primes not exceeding a specified positive integer. So we'll see this example. So what is the example? We want to find, the example is find the number of primes, find the number of prime numbers. So primes over here is prime number not exceeding 100, not exceeding 100. Okay, so first we have to note that the composite integers not exceeding 100 must have a prime factor not exceeding 10. Now what does this mean? So if we have a composite number, suppose our composite number 50 is a composite number, yes. What are the prime factors of 50? The prime factors of 50 will be, so 1 will divide 50, okay, 1 is a prime number, 2 will divide, yes, 2 is also a prime number. What about 3? No. 4? No. 5 divides 50, 6, 7, 8, no, they won't divide, then 10. So 1, 2, 5, all of these, 1 is neither considered prime nor composite. So we'll start with 2 and 5. 2 and 5, both of them are prime numbers and they are less than 10. So whenever we are talking about composite numbers, the value of the prime factors will be less than 10. Okay, similarly, if we even take 99, we will have 1, 3, then we have 9. Okay, so 3 and 9, these are the 3 is a prime factor which does not exceed 10, while 9 is composite. So 3 is a prime factor which does not exceed 10. Apart from that, after 3, all the numbers which we consider will be composite numbers. So generally, whenever we are talking, the rule is that the composite integers not exceeding 100 must have a prime factor not exceeding 10. Now, let me me write that rule actually. So the important point is composite integers not exceeding 100 must have a prime factor not exceeding 10. Now what are the prime numbers not exceeding 10 or the prime numbers less than 10? The prime numbers, let me write here, prime numbers less than 10 are given as follows. They are 2, 3, 5 and 7. So these are the prime numbers less than 10. Now what are we supposed to consider? The prime numbers not exceeding 100 are these 4 primes, and all these positive integers greater than 1 and not exceeding 100 that are divisible by none of 2, 3, 5, 7. So the number of primes not exceeding 100, so we have to find prime numbers. So the numbers which are not divisible by either 2 or 3 or 5 or 7 will be the prime number not exceeding 100. So to apply the principle of inclusion exclusion on this, so it will be solved in this way. Let P1 be the property that an integer is divisible by 2. P1 is the property divisibility by 2. What is it satisfying? Divisible by 2. Similarly, P2 is the property divisible by 3. P3 is the property divisible by 5. And P4 is the property that it is divisible by 7. Thus, the number of primes not exceeding 100 is, so 2, 3, 5, 7 themselves are primes, so these are 4 numbers, plus the numbers which are not divisible. So P1 was divisibility by 2. So P1 dash will be not divisible by 2. P2 dash is not divisible by 3. P3 dash is not divisible by 5 and P4 dash is not divisible by 7. So the total numbers not divisible by 2, 3, 5, 7 plus the prime numbers themselves. Now we have to find this term. What is this term? So there are totally how many positive integers greater than 1? There are 99 integers between 1 and 100 and not exceeding 100. So we won't count 100. Now the principle of inclusion exclusion, what will be the formula? N of P1 dash, P2 dash, P3 dash, P4 dash. What are the total numbers? We have 99 numbers minus. Now we have to expand our formula for P1 union P2 union P3 union P4. Now this formula I have done it in the last lecture, that is find the principle of inclusion exclusion for 4 sets. So how was this formula? How is this formula? It can be written in the following way. So 99 minus whatever were the positive terms will become negative and vice versa. This you can easily understand. So I'll just write the formula directly. So n of P1 denotes the numbers which have the property P1. So n of P2 are the total numbers which have the property P2. In this way, n of P3 minus n of P4. After that, we were taking the intersection, if you remember, P1 intersection P2, A intersection B, B intersection C, and so on. And we had 6 terms of intersection. So now those intersection terms of 2 sets were negative. In this case, we will have them as positive because we have already having the negative sign. So plus n of the numbers which have the property both P1, P2. So I'll just write it in this way. P1, P2 plus n of P1, P3 plus n of P1, P4, n of P2, P3, n of P2, P4, and finally n of P3, P4. So these are in total 6 terms. After that, we have to take intersection of 3 sets. We'll have 4 terms of that. So what are the 4 terms? Minus. In that formula, we had positive, but because of the already existing negative sign, it will become negative. N of P1, P2, P3 minus n of P1, P2, P4 minus n of P1, P3, P4 minus n of P2, P3, P4 plus n of P1, P2, P3 and P4. Okay. So this is the entire formula. Now for this formula, we have to find what is the property P1, how many integers are divisible by 2. So if you remember, this was the first problem. If you had divisibility with 3 and 5 or 5 or 7, one of the problem was solved. So we'll just do it directly over here. So 99 minus n of P1, I'll just write it over here. N of P1 will be number of integers divisible by 2. So what are the total number of integers? 100. So 100 by 2. We have to take always the floor value whenever we are doing the divisibility. So 100 by 2 floor value. So in this case also we have to take 100 by 2. What will be n of P2? Divisibility by 3 minus 100 by 3 minus 100 by 5 and minus 100 by 7. Now this is simple because we have 4 numbers. Property is divisibility by 2, 3, 5, 7. We have done that. What will be the next one? Where we have n of P1, P2. So in this case, we will have divisibility by 2 and 3. So we have to look over here. Divisible by 2 and divisible by 3. So 100 by, it should be divisible by both 2 and 3. What are the numbers divisible by both 2 and 3? The numbers which are divisible by 2 and 3 are also divisible by 6. So we will take it in this way. Minus 100 by 2 into 3. Actually, we will have it over here. The symbol is plus. So we will have plus over here. Plus 100 by 2 into 3. Then the next thing was P1, P3. Divisibility by 2 and 5. So over here, 100 by 2 and 5 plus 100 by 2 and 7 plus 100 by 3 and 7 and 100 by 5, 7. So these are the 6 terms. 2, 3, 2, 5, 2, 7. Yeah, one term is missing, which is 100 by 3 into 5. So intersection of 2 sets will have 6 such combinations. And then we have to move on to the 3 sets. So we had over here P1, P2, P3, P1, P2, P4 and these ones. So those are with a negative sign. So 100 by 2 into 3 into 5 minus 100 by 2 into 3 into 7, the floor value, 100 by 3 into 5 into 7, and one is missing, which is 100 by 2 into 5 into 7. Okay, so these are the intersection of sets with 4 values. And then lastly, we will have the term which is the number which is divisible by all 2, 3, 5 and 7. So that term will be taken with a positive sign. Why? Because we have plus n of P1, P2, P3, P4. So let's just write that. The floor value of 100 by 2 into 3 into 5 into 7. Okay. Now, how many numbers are divisible by 2? So 100 by 2 will give you 50. The floor value is 50 anyway. So 99 minus 50. The number is divisible by 3. So 100 by 3, it goes 33 times. 33.33 actually. So this we have to take the floor value. So we'll take 33. 100 by 5, 20. No need of the floor value. 100 by 7, it will give us 14 point something. So we have to take the value 14, floor value. Now after that, 100 by 6. So 100 by 6, it goes 16 times, 16 point something. So we'll take plus 16. 100 by 10, directly we know the value is 10. Similarly, you can just solve it. So plus 7, plus 6, plus 4, plus 2, minus 3, minus 2. Now, in this case, 100 by 3 into 5 into 7. So 15 into 7. Okay. So 3 into 5 into 7, 15 into 7 will be 105, I believe. and 100 by 105, it will give us 0 point something. So this will be 0 minus 0, 2 into 5 into 7, 70 one time, so minus 1 again, plus 2 into 3, 6, 6 5 were 30, 30 into 7, 210, 100 by 210, it will give us again 0. Okay, so this is the total value. Now when we solve the entire numbers, we will get the value 21. So 21, and what was the number of total primes? 4 plus whatever value we get for this term. Okay, so 4 was 2, 3, 5, 7 already we have taken, plus the total numbers. So 4 plus 21, this will give us 25. So there are 25 primes. Let me just write it over here. 25 primes not exceeding 100. So the prime numbers less than 100, total number of prime numbers less than 100 is 25. Okay. Now, so the same formula has been written a bit more clearly over here. So, and the problem that we have done, the finding the prime numbers, that is E of Eratosthenes. Now we have the next example or the next application, which is the number of onto functions. So the principle of inclusion exclusion can also be used to determine the number of onto functions from a set with m elements to a set with n elements. Okay, so if we have to find the number of onto functions, and we have a set with m elements on to a set with n elements, so m is to n, then how many onto functions are there from a set with, let's just do it again over here. So how many onto functions are there from a set with 6 elements to a set with 3 elements? So suppose the elements in our codomain, so these are B1, B2 and B3, and let P1, P2 and P3 be the properties of this B1, B2 and B3, and that are not in the range of the function respectively. Note that a function is onto if and only if it has none of the properties P1, P2 or P3. So whenever we are mapping, if you remember, onto function is, what is the definition of onto function? If you remember, the definition of onto function is, in function f from a to b is onto if for every element if we have f of a is equal to b. That is, a mapping from the domain to the codomain should be done in such a way that every element should be mapped. So then that is known as a onto function. Now, in this case, a function is onto if and only if it has none of the properties P1, P2 and or P3. So by the inclusion exclusion principle, we can write it in this way: n of P1 dash, P2 dash, P3 dash is written as n minus, again, n of P1 plus n of P2 plus n of P3. Over here the overall negative sign is taken, plus n of P1, P2 plus n of P2, P3 and so on. We will write it in that way. So plus n of P1, P2, and I have just taken the negative sign for those three terms and then the positive sign, alternatively negative positive if you recall. P1, P2, P3, where n is the total number of functions from a set with 6 elements to one with 3 elements. So a set with the total number of functions from a set with 6 to 3 elements will be 3 power 6. N is equal to 3 power 6. Now, what will be the total number of functions? 3 power 6 minus. The formula is, if n of pi is the number of functions that do not have the codomain bi in their range, hence there are two choices. Okay, so there are 3C1 kind of ways and we have two choices to do the selection. So the general formula is taken as, in this case the general formula will be taken as n power m minus Cn1 into n minus 1 power m. Why are we taking n power m? This is the total number of functions, as I have just explained. Now, what is this? If we are making the choices in such a way that we are excluding the property P1, okay, we are taking the property P1, so 3C1 into what are the other choices we have to fill the m blanks? We have n minus 1 ways, okay. Similarly, if we are taking only the property 2, then we have n minus 2 ways to fill the blanks, and this is the formula. Actually, this is a theorem which needs to be remembered. So over here, if m and n are the positive integers in such a way that we are creating an onto function from a set with m elements to a set with n elements, then this is the formula: n power m minus nc1 into n minus 1 whole power m plus nc2 into n minus 2 whole power m, and so on. How did we get it? We have derived it by using the formula n of p1 dash, p2 dash, p3 dash, and so on up to pk dash. Then it will be total number of functions minus the functions which have the property p1 plus n of p2 plus n of p3 in this way. Okay. So now, if we are solving the earlier problem, so assume m is equal to 5, n is equal to 4, then by using that formula, we'll have 4 power 5 is the total number of functions minus 4c1 into 3 power 5 plus 4c2 into 2 power 5 minus 4c3. Already in this formula also we'll have alternatively positive and negative sign, minus 4c3 into 1 power 5. Once we get 1 power 5, that is, once we get the value 1, we will stop, because as naturally the next term will be 0. So this is another application of principle of inclusion exclusion, the number of onto functions. Apart from that, the last application is derangement. Okay, what do you mean by derangement? So I've explained the hat check problem. So suppose if in a office or a movie theater, the persons check their hats. Each person is wearing a hat and they check their hats, and people are checking their hats, and they're in the checking counter. When the hats are being returned, the condition is that each person is not getting their own hat, they are getting someone else's hat. So when the persons are returning for their hats, the checker gives them hats chosen at random, and what is the probability that no one receives the correct hat? That is your hat check problem. So that problem is based on this concept, derangement. What do you mean by derangement? A derangement is a permutation of objects that leaves no objects in its original position. So the number of derangements of a set with n elements is given directly. We have a formula. So if we have 3 elements, if I take the numbers 1, 2, 3, I said there are only 2 derangements. What are the derangements? 2, 3, 1 and 3, 1, 2. These are the 2 derangements. So the number of derangements of a set with n elements is given by this formula. Let's apply it on these numbers. So the number of derangement of a set with 3 elements will be B3 is equal to 3 factorial into 1 minus 1 by 1 factorial plus 1 by 2 factorial. Wait till where we have to continue till we get n factorial. So minus 1 by 3 factorial. So 3 factorial gives you the value 6. 1 minus 1 by 1 factorial is 1 plus 1 by 2 factorial will give us 2 minus 1 by 6. So this is cancelled. 6 into 1 by 2 minus 1 by 6. So it will give you the answer 2. So the number of derangements with 3 elements is 2. Similarly, if we want to find over here, we can take another example. So the example is the permutation. If we have 1, 2, 3, 4, 5, then 2, 1, 4, 5, 3, it is a derangement of 1, 2, 3, 4, 5, because no number is left in its original position. And how many derangements you will get, you can find out by finding out the value for D5. We have 5 elements, and by finding D5, you can find the number of derangements. For this, you can solve it as a homework problem. So this concludes the topic applications of inclusion exclusion.